Very good. The meeting's being recorded. This award is really an absolute honor, and it really is very, very humbling. It also gives me a nice opportunity to say a quick thank you to everyone in our community who makes this such a fun area to work in, and especially to my mentors and my collaborators over the years as I found my way into this community, starting from the Adelaide crew, Ross, James, and Tony, to my wonderful collaborators in NPL QCD, and especially Will, who was just so much fun to share an overlapping group with at MIT. And of course, John and my group of absolutely awesome students and postdocs whose faces you'll see on some of my slides. Okay, so before I start, the brief for this talk was a colloquium to a broad demographic, but with a reality of a mostly Lattice audience. So I have to start by apologizing to the Lattice crowd for the extended introduction and apologizing to everyone else for a few extra technical details that I let slip into some of the slides for the experts in the room. So the topic of this talk is broadly the structure of matter, and in particular, the structure of the protons, neutrons, and nuclei that we know make up the majority of the visible matter in the universe. Our modern understanding is, of course, that the protons and the neutrons in an atomic nucleus have substructure. They're made of matter particles called quarks, held glued, bound tightly together by the strong force manifesting as force-carrying particles known as gluons. And to the best of our current understanding, quarks and gluons are it. They are fundamental particles and they can't be divided any further. The quarks and the gluons and their interactions are encoded in the standard model of elementary particles. Now, this framework, which was put together in the 1970s, has just 17, you can see them here, just 17 fundamental particles, and it describes 3 of the 4 fundamental forces, so notably excluding gravity, in this very elegant and beautiful, very symmetric, very predictive framework. And in fact, a number of the standard model particles were predicted before they were seen experimentally. Most recently, I think many of us will remember the Higgs boson in 2012. Now, this framework is an extraordinarily successful description of the matter in our universe, which has withstood almost every experimental test. And just to give some sense for that, here's an example: the magnetic moment of the electron. That's how much torque an electron feels in a magnetic field. What I'm showing here is the anomalous magnetic moment, the deviation from the tree level or classical result. This is the most accurately verified prediction in the history of physics. And for any graduate students in the room, you'll understand the heroic effort that's needed for up to 5 loops of Feynman diagrams. That's 30 years of effort to calculate these 12,000 Feynman diagrams to give this result to 12 significant figures that agrees between theory and experiment. But it's not just that the standard model is successful at sort of certain key predictions, it's that it's successful over such a wide range of scales. So here's just one other example in deep inelastic scattering. So that's scattering where you take an electron and fire it at a proton so hard that the proton breaks apart. This is encoded in what are called structure functions, shown here in this chart. And on the horizontal axis, we have energy on a logarithmic scale. So this covers many orders of magnitude here, this figure. And you can see a consistency between the experimental results, the points here, and the theory predictions, which are the yellow bands. So, but of course, we also know that this extraordinarily successful and predictive theory doesn't describe everything we observe in our universe. And just one example that we'll get back to later in the talk is dark matter. We in fact know that the matter described by the standard model is just this tiny sliver of the energy density pi, and that most of the matter in the universe is something else. We also, of course, know that neutrinos have masses, but they don't in the minimal standard model. There's an asymmetry between matter and antimatter that we can't explain. How does gravity fit in? There are naturalness questions. Why is there this big discrepancy between the weak and gravitational scales? So clearly there is physics beyond the standard model, and we're always seeking to constrain that better to understand the physics that we don't know. And just one class of experiments searching for physics beyond the standard model is particularly relevant to the discussion of this talk. And that's experiments at what we call the intensity frontier. That's experiments where we're looking to probe the rarest standard model interactions and look for beyond standard model effects. So things like dark matter direct detection fall into this category, neutrino physics, many other examples. And what these experiments have in common is that because we're looking for these really rare interactions for signs of new physics, you want to increase the cross-section as much as possible. So they use nuclear targets. And so to understand physics beyond the standard model, to constrain it in these experiments, we also need to understand the standard model physics of the protons and the nuclei in the targets in those experiments. So when I'm discussing understanding the structure of matter, of protons and of nuclei from quarks and gluons, there's really several reasons. The first is for its own sake, to understand the emergence of all of the complexity in nature from this beautiful, elegant theory of the standard model. And the second is that since we know the standard model isn't everything, we need to understand it better to constrain searches for new physics. So this really lines up with the award citation and also forms the outline for this talk. I'll give some examples of first principles theory studies to study the structure of the proton and of nuclei, and also how advances in computing and algorithms are accelerating and enabling this work. So a little bit more introduction. The hard part of this is, of course, the study of the strong interactions described by the theory of quantum chromodynamics. The strong interactions are the strongest of the four forces in nature, and of course, they're responsible for binding quarks and gluons into protons and neutrons and binding protons and neutrons into nuclei. So if we're interested in the structure of those protons and nuclei, the strong force is key. But studying it is complicated by the fact that at low energies, so the energy scales relevant to the structure of, say, a nucleus at rest, the strong interactions are non-perturbative. So here we have the strong coupling constant. On the horizontal axis is energy. And as we come to the left here, to low energies, the coupling strength grows. And what that means, of course, is that you can't expand in powers of that coupling strength. You can't do a perturbative solution. So we need to do something non-perturbative, and that's where lattice field theory comes in as the only known systematically improvable way to study the strong interactions from first principles. And the idea is quite straightforward to say, less straightforward in practice, that we take the equations of QCD and write them for a discrete space-time grid. And then the path integral becomes essentially integrals over the values of the quark and gluon fields at each site or link on the lattice. So this is a very high dimensional integral, something like 10 to the 12 variables. And we evaluate that integral by importance sampling, which is again easy to understand. You can just think about quantum mechanics if you like, that we know that paths near the classical action dominate, and so we can sample those proportionately more than the less important paths. So to put it in just a little bit more of technical detail, we have a Euclidean space-time lattice with, of course, some non-zero lattice spacing and some finite volume. And you have to take the limits as the spacing becomes small, the volume becomes large to match to continuum QCD. And some calculations, and some of the ones I'll talk about, use larger than physical quark masses simply because it's computationally more efficient. You have to invert a lot of matrices that get close to being singular as the quark mass gets lighter. And then here, if we just write out the expectation value of some observable, here's the QCD path integral with our integrals over quark and gluon fields. In this important sampling approach, we sample the field configurations with this weighting, the exponential of the action built in. And then computing observables becomes just taking essentially averages and standard deviations over that samples. And some of the challenges in this sampling are what questions we'll come back to at the end of the talk. So just to summarize, really, in lattice QCD, the input parameters, the free parameters, are the same as the free parameters in QCD. That's the quark masses and the strong coupling. And once those are fixed by matching to some of the measured hadron masses, and with one additional experimental input to fix the lattice spacing or the strong coupling, then everything else, from the details of the structure of the proton to the structure and interactions of nuclei, are predictions from the theory. There's no additional modeling. And these calculations are really computationally expensive, as you might imagine, from the very large dimensionality of the integrals. They use many millions of CPU and GPU hours. Just to give some scale, some of the calculations I'll describe would have taken something like 30,000 years on my laptop. Here's Summit, currently the world's largest supercomputer. And if every person on Earth did one computation every second for a year, that's about what Summit can do in a second. So just for a sense of scale. And of course, as the lattice field theorists in this room very well know, lattice QCD works. And we're really in a precision era of lattice field theory for simple quantities, for properties of single hadrons, for example. Over the last 5 years or so, we've really seen examples of the ground state hadron spectrum being reproduced, a nice calculation of the proton-neutron mass difference, including both QCD and QED. And so you can really see in a theory calculation how the competing effects of the strong interaction pushing that mass difference one day and the electromagnetic effects pushing it the other way cancel to give us this small but critically important mass difference in nature. Predictions for new states with controlled uncertainties. For example, here, all of the blue points are states predicted from lattice QCD. The red lines are from experiment, and this additional red line, state found by LHCb after it had been predicted. And of course, when we talk about more complicated quantities, such as quantities for nuclei, we're not in this precision era yet. And that's because nuclear physics in this framework is really just computationally very hard. The noise, the statistical uncertainty grows exponentially with the number of nucleons in the calculation. The complexity grows factorially. So we have these compounding exponential and factorial challenges. And so calculations at this stage are possible for atomic number A less than about 5. So the nuclear physics calculations I'll talk about are done with the NPL QCD collaboration. Of course, there are also other collaborations around the world also working on lattice QCD studies of nuclei. And I'll only have time to briefly highlight a couple of latest results from that collaboration. Okay, so after the extended introduction, coming back to the first topic, the emergence of the complex structure in nature, that is understanding the quark and gluon structure of matter. Now, of course, I'm discussing this from a theory perspective, but there's a great synergy between experiment and theory, which we'll see some examples of. And understanding the quark and gluon structure of matter really is a defining effort in experiments, with experiments around the world having the same goal. So one place to start is talking about the three-dimensional platonic, that is the quark and gluon structure of the proton. And there's a really nice community overview this year of lattice QCD contributions to this area. And I'll give just a few examples, primarily from my own recent work. So if we're thinking about the quark and gluon structure of the proton, we encode that structure in a number of distributions. So one of the simplest we can think about is the parton distribution functions here. These Fs, these are the number densities of quarks or gluons of some flavor F in the hadron H, say the proton, carrying some longitudinal momentum fraction X, so some fraction of the longitudinal momentum of that proton. If we also consider the transverse structure, so add in our additional transverse scale, we call them transverse momentum dependent parton distribution functions. And we can also allow a momentum transfer. So this psi is a skewness, it's a longitudinal momentum transfer. We get generalized parton distribution functions. And I'll talk about some aspects of each of these. So starting with the PDFs, the parton distribution functions sound complicated, but the moments in particular encode some very key and intuitive aspects of hadron structure or proton structure. So the moments are these X-weighted X integrals, where again, X is the longitudinal momentum fraction carried by that parton. And the lowest moment describes the contribution of each parton to the momentum of the hadron. And there's this nice highlight this year of the proton momentum decomposition by Dean Alexandru and collaborators, where they've calculated each contribution up, down, strange, charm, and gluon contributions to the proton momentum and see that they add up to 1, as of course they must. And lattice QCD can cleanly access low moments of parton distribution functions. And it would be remiss of me to mention PDFs without saying that, of course, there's massive community efforts to also study the X dependence, that momentum dependence from lattice QCD with various approaches. But coming back to the moments for the moment, we can also use lattice QCD results for the moments and include those constraints to global fits to experimental data. So again, a synergy between theory and experiment to better understand the parton distribution functions themselves. And there's this nice example from a few years ago showing this exactly for the transversity parton distribution functions, which are less well constrained from experiment, especially at large X, so large longitudinal momentum, and the flavor separation is not complete. And just by including the lowest moment of the parton distribution functions calculated in lattice QCD, you go from these yellow bands to these smaller blue and red bands. So adding that one number gives you a much better constraint on these parton distribution functions. And here the fragmentation function which you can think of as being the final state analog of the initial state parton distribution function. So the probability that the hard parton called I here will fragment into some hadron carrying some fraction z of parton momentum. So one of my interests is extending this great success of lattice QCD to nuclei. So of course, we can also ask this about nuclei, and it's one of the simplest and most intuitive questions you might ask about a nucleus, is how is the partonic structure, that's the distribution of quarks and gluons in nuclei, different from that of a collection of nucleons? So of course, we know that a nucleus is not just a collection of nucleons stuck together. We can call these sorts of effects, these nuclear effects, EMC type effects, in the honor of the European muon collaboration, who saw in 1983 that deep inelastic scattering of a nucleus doesn't just look like the sum of deep inelastic scattering of the constituent nucleons. So here's the DIS cross-section ratio per nucleon for iron to deuterium versus this longitudinal momentum fraction x, and you see that this is clearly not one. So evidence of nuclear effect. So we can start to get at the EMC type effects from lattice QCD by looking again at these simple quantities where we have such success in calculating them precisely for protons in the lattice field theory approach. So we can look, for example, at the momentum fraction carried by quarks of different flavors in light nuclei. So this is recent work from the NPL QCD collaboration where we've calculated the up minus down quark contribution to the momentum fraction in helium-3. So this calculation was done at larger than physical quark masses corresponding to a pion mass of about 800 MeV. Then we had to extrapolate by constraining the low energy constants of effective field theory and extrapolating to physical quark masses. But after you do this, you still have a result here with the red band, which is a constraint on this momentum fraction. The best experimental, the global fits to experimental data from the NNPDF collaboration is this blue, light blue ellipse here. So you can include the lattice QCD constraint, just like we saw for the proton, into this global experimental fit and improve the constraints and go to this purple ellipse here. And so even though we're really in the very beginning of these sorts of studies for nuclei, we can already see that there's great potential for the sort of success we've seen in the study of single hadrons to extend to nuclei. We can then also do the same trick, of course. What about including this constraint on the moments to see what you can do for the PDFs themselves? And you can see that even this constraint gives us an improved parton distribution function. This is actually the ratio of the parton distribution function of helium-3 to that for the proton. An improved constraint by including the theory result into the global fits to experimental data. We can come back to this discussion of proton structure and talk not just about the longitudinal structure, but what if we also think about the transverse structure? And of course, there's been a lot of work in the community, particularly by Michael Engelhardt and collaborators, to compute TMDs themselves from lattice QCD. I'll talk just about one calculation done with Mike Wagman and Yong Zhao of the Colin-Soper evolution kernel. So this is a quantity that governs the rapidity evolution of these TMDs. It governs the dependence on this hard scale, which is related to the momentum of the hadron, or equivalently to the hard scale of the scattering process. And this evolution is, of course, needed to match TMDs measured at different scales. It's also needed if you're trying to match quasi-TMDs. So that's the framework we can use for accessing TMDs, one of the frameworks we can use for accessing them on the lattice, to physical TMDs. And this quantity is perturbative at short distances, but it becomes non-perturbative at longer distances. And so, of course, that makes it a key target for the non-perturbative tools we have in lattice field theory. So it's been shown that you can access this Colin-Soper evolution kernel via a ratio of non-local matrix elements. And this is where I'm getting a bit technical for a physics colloquium. And some examples of these non-local matrix elements, these quasi-beam functions, are shown here on the right of the slide. And so we followed this calculation through in a first quenched calculation this year. Since this kernel is independent of state, we could study a pion, and since it's a quenched calculation, we could even study an unphysically heavy pion with no systematic effect. to calculate this evolution kernel. And that's what I'm showing here. And here's this transverse scale on the horizontal axis. These lines here are the perturbative results. They become singular about here because they reach the Landau pole. And what you can see is that we have reasonably precise results up much further than the perturbative results can reach. And if you do a comparison between these results to phenomenological models, and of course this deserves a significant word of caution. This is just a Photoshop overlay of phenomenological models, which are of course not quenched, so not zero flavor, with the zero flavor lattice calculations. What you can see is that systematically controlled results at this precision would already impact phenomenology. So this is preliminary work with, again, lots of promise in this area. And then we can come back and say, well, what about the generalized Parton distribution functions? And again, I can give a nice example here. If we think again about, like we thought about the moments of the Parton distribution functions, we can think about the moments of the generalized Parton distribution functions. And what these describe are generalized form factors which encode, for example, matrix elements of the energy momentum tensor. So the moments of the generalized Parton distribution functions give us these things here, these generalized form factors. What I'm showing here are matrix elements of the gluon traceless energy momentum tensor in a nucleon state. And if you decompose those matrix elements just into its Lorentz structures, you have these a priori unknown coefficients, which you can relate to the moments of the generalized Parton distribution functions. To give some physical intuition, if we look in the forward limit, so where we have no momentum transfer, so when P and P prime here, your initial state proton and your final state proton have the same momentum, then these moments reduce just to the moments of the Parton distribution functions that we saw before. So this A here with a zero momentum transfer, which is P, with P equals 0, just looks like the momentum fraction. So how much momentum is carried by the quarks and gluons in the proton. The A and B are related to the spin. And then we also have the D, which are called the D terms, which are largely unknown, but equally fundamental. And then if we include this generalized part, the momentum transfer part, and look at the T dependence, then these D term generalized form factors, you can think of those in a nice way. You can think of them as encoding pressure and shear distributions in the proton. And so this is an example where we can have a nice physical picture. So quarks are, of course, confined inside protons. So if you think you have a pressure distribution, then any expanding forces have to be cancelled by compressive forces for stability. So we can draw a cartoon. What I'm showing here is the radial distance out from the center of the proton, that distance squared times the pressure. And here on the horizontal axis, that radial distance out from the center of the proton. And you can see that this is the quantity that has to integrate to 0 for stability. So if we make a cartoon and say there's a repulsive pressure at the core of the proton balanced by a confining pressure as you move out further along the radius, we can ask some questions about this distribution, such as how do quarks and gluons contribute? What's the radial extent of the pressure distribution? What's the peak? Is it more like a bike tire that's 10 to the 5 Pascal, or is it more like a neutron star at 10 to the 34 Pascal? What's the pressure inside the proton? And so this has been particularly interesting in just the last couple of years, since there was a first experimental extraction of the pressure distribution in the proton. And what they found in that study was that the peak pressure near the center of the proton was in fact greater than an order of magnitude greater than that at the interior of a neutron star, so the densest known objects in the universe. But the experiment through deeply virtual competence scattering was only sensitive to the quark contributions to the pressure and not to the gluons. So to make these conclusions about the proton's pressure distribution, one had to assume that quarks and gluons contribute to the pressure in the same way. So what we were able to do was compute the gluon generalized form factors and hence the gluon contribution to the pressure distribution, and see that gluons change this picture, and also to really explore what will be needed in future experiments like an electron ion collider to measure the gluon contribution to the pressure from experiment. So what you see here is the same as the cartoon I just showed. This is that radial distance squared times the pressure distribution. On the horizontal axis, the radial distance from the center of the proton. The blue here is what you get from the experimental result, assuming quarks and gluons contribute the same way. And in red, you have the total taking the quark contributions from experiment and the gluon contributions from lattice theory and putting them together for a first complete pressure determination. And you see that gluons change the picture. The peak is shifted. We have the tail is extended by including gluons. Gluons are, of course, important in the pressure in the proton. So we can also ask, well, how does this pressure distribution compare to that in other hadrons? Can we get some intuition on what this means? So these pictures look a bit nicer because I'm showing just lattice results with a heavier than physical quark mass here, but it's the same idea. This is the pressure in the proton. Here we have the pressure in the pion. And what you see is that although if you look just at the simplest static quantities, like the momentum carried by quarks and gluons in the proton versus the pion, in each case, they're quite similar. Quarks and gluons carry about 50% each of the momentum of the proton and also of the pion. If you go add the extra dimension and look not just at the single quantity, but at this distribution, you see they have quite different pressure distributions. The one for the pion has a higher peak and a much shorter radial extent. And so we can also ask, well, what about other hadrons? And so new studies of the rho and delta at heavy quark masses and also the nucleon and pion at physical quark masses will be coming soon, led by grad student Dimitri Pevcu and Dan Hackett, who's a postdoc at MIT. We can also ask, of course, well, what about light nuclei? And maybe you might think that calculations of pressure inside nuclei could be connected to equation to states of neutron stars in some way. And this is, of course, work that's also on the horizon. Okay, so we can also come to this question, well, what about more directly the impact of these sorts of calculations for searches for new physics? Of course, I should have said that all of the other results also have implications for searches for new physics, for example, the parton distributions and the Collins superkernel at the Large Hadron Collider. But let's talk more explicitly about the example of dark matter. So, of course, there is abundant evidence for dark matter, from galactic rotation curves to gravitational lensing to structure formation to evidence in the cosmic microwave background. And we know that about 5 times as much of the energy density of the universe is carried by dark matter as compared to normal matter that we can describe so successfully with the standard model. There are many, many models for dark matter, but relatively few constraints at this stage. And I like to show this nice figure from Tim Tate, sort of trying to map the various different theories and models for dark matter, from axions to sterile neutrinos, extra dimensions, supersymmetry, little Higgs, and it goes on, right? And what we need to really understand dark matter better is constraints in this space. Of course, there are many ways that we try to constrain the properties of dark matter, and I'll mention just one, and that is in direct detection experiments. And so this is where, of course, dark matter is dark. It doesn't interact with light. It does interact through gravity. That's how we know it's there. But maybe it interacts very weakly through the weak interactions. And then we might think that if we have a detector deep underground, so it's isolated from everything else, we might be able to see direct interactions of dark matter with our terrestrial detectors. So this is the dark matter direct detection program, looking for, say, weakly interacting massive particles, for example. And then the detection rate, of course, depends on the properties of the dark matter, which is what we're trying to constrain, and also the probability that the dark matter interacts with the nucleus. Okay, so these sorts of experiments, we don't have evidence for dark matter yet, but you can set limits on the interaction strength of dark matter candidates with nuclei. And what these limits look like is something like this in a figure, where on the horizontal axis, we have the mass of our proposed weakly interacting massive particle. And on the vertical axis, we have the limits on the cross-section for these weakly interacting massive particles to interact with the proton or neutron, with the nucleon. And the way to read these plots is that everything above these lines, each of these lines comes from some experiment. All of that phase space above the lines is ruled out. And here below is the still available phase space for dark matter to live. What I want to emphasize here is that these experiments all use large nuclei. For example, here, xenon 1 ton uses xenon. It's a nucleus with 130, 140 protons and neutrons. But what we're showing here is the spin-independent, that's what SI means, WIMP nucleon cross-section. That's the cross-section for interaction with a proton or neutron, which is, of course, what we'd like to constrain. So what's happened implicitly here is there's been a translation between not seeing dark matter hit xenon to what that means for its interaction strength with a single proton or neutron. And the simplest way to do that translation is, of course, to use the Born approximation. And that's just the approximation that when your dark matter comes in and it hits the nucleus, it hits a single proton or neutron at a time. So you just scale your interaction of your dark matter candidate with a proton or neutron. This is something you can calculate precisely in Lattice QCD. You just scale that by the atomic number, and then that gives you the cross section. But of course, well, what if the dark matter interacts non-trivially with multiple nucleons? Then you don't just want the interaction with a single proton or neutron, you also want this matrix element for its interaction with multiple protons or neutrons. And the second term could be significant, and it could scale differently with Z and with A. And this can lead to significant uncertainty. So this is, again, an NPL-QCD collaboration result where we studied the spin-independent scattering of these WIMP candidates. Of course, we don't know the microscopic theory of WIMPs, but the low energy limit of a generic spin-independent interaction is scalar, coupling to any quark flavor. So what's relevant are the scalar matrix elements. And so we calculated in a calculation with a larger than physical value of the pion mass, these scalar matrix elements in light nuclei. And what we saw was really larger than anticipated nuclear effects. So what's being shown in this figure here is this quantity, the ratio of the matrix element in a nucleus to A times the matrix element in the nucleon minus 1. So this is just 0 if you have the Born approximation holding. So deviations from 0 here are what are revealing nuclear effects. And each of these columns is a different combination of quark flavors. So here up minus down, here up plus down plus strange, and so on. And what you see here for these green points, this is helium-3, you see nuclear effects around the 10% level. So to put this in context, this is large. You can look at, say, the axial matrix elements where we can measure them in nuclei, and we know that in medium mass nuclei, the nuclear effects in the axial matrix element are tens of percent. But in helium-3, they're very, very small. They're a fraction of a percent. Whereas here we have the scalar matrix elements having 10% effects even in helium-3. And of course, these calculations are not systematically controlled, larger than physical value of the pion mass. But what this says is that these unexpectedly large multi-body effects really shouldn't be neglected in the interpretation of dark matter direct detection experiments. And it's really crucial to do a systematically controlled study. And so we have a calculation at almost physical quark masses in progress on this front. So, of course, I talked about direct detection experiments with xenon. Of course, we would also love to know the matrix elements and the QCD structure of larger nuclei, which are in many cases phenomenologically relevant. So the way to constrain those is via nuclear effective theory, where one body currents are dominant, two body currents are subleading but non-negligible. You'll note that I said a two body effect of 10% was sort of unexpectedly large, so that you still have a hierarchy. And so the program is really to determine the one body contributions from single nucleon calculations, few body contributions from calculations with two body, three body, four body states, and then match effective field theory and many body methods to lattice results to make predictions for larger nuclei. But of course, we can also ask, well, what are the real barriers to studying larger nuclei? And a key aspect is just computational, that we have exponentially harder problems computationally, and so you'd like exponentially improved algorithms. And just to give some examples of the real case for trying to study and constrain matrix elements of large nuclei. The June long baseline neutrino experiment, which is looking to measure the neutrino masses, the neutrino mass hierarchy really, and the oscillation parameters, is doing neutrino scattering on argon. That's A equals 40. So you really want to know the actual form factors of argon and how big the nuclear effects are on those. Looking for double beta decay, so for telltale signs of whether the neutrino is its own antiparticle or not. The lightest nucleus that undergoes double beta decay is A equals 48. I gave the example of the scalar matrix element, xenon, A equals 131. We'd love to constrain that. So there's real physics cases for trying to study light nuclei and heavy nuclei. But we face computational challenges. So this brings me to the last point. So how advances in algorithms can, of course, enable physics calculations that wouldn't otherwise be possible. And I'll give just one example of something that my group's been focusing on recently, is trying to accelerate the generation of QCD gauge field configurations. So the problem is quite simple to state, that we want to generate these field configurations with a known probability distribution given by the exponential of the action. Yeah. And what we typically do is we use Hamiltonian or hybrid Monte Carlo. It's a scheme where we update from one configuration to the next. It's a coupled walk in position and momentum space through Hamiltonian dynamics. And because it's an update, right, from one configuration to the next, you have some correlations between configurations in your chain. So you have some amount of burn-in time, and then you're still generating correlated configurations. So you want to sample every nth configuration, where n is dictated by the Markov chain autocorrelation time. And having a shorter autocorrelation time means less computational costs to generate independent configurations. So a particular challenge with this is that these updates are, in a sense, diffusive or close to local. So you can think that if you're trying to update physics to generate independent configurations on some physical length scale, say the size of a proton, then as the lattice spacing becomes fine, the number of steps you need to take to decorrelate physics on that fixed scale diverges. So you need to do more and more updates to affect the correlations on that scale. So this is a manifestation of critical slowing down in this context. And this is a particular computational challenge. So if we come back to looking at this problem, what we'd like to do is generate these field configurations with some known probability distribution. So let's visualize this. In a scalar field theory, so just a number at each lattice site, we can visualize this very nicely. We would like configurations that look like this and not like this. So this is just random noise. This is very unlikely. These are likely configurations. They have characteristic correlations on a characteristic length scale. I should thank grad student Tej Kanwar for some of these nice figures. Generating configurations like that has some parallels with an image generation problem that's received a lot of attention from the machine learning community and a lot of great success. So there's been a lot of success in generating images like this. So these are not photos, they are machine generated images of faces. You can go to www.thispersondoesnotexist.com and refresh, and it will give you a new fake person every time. And so there have been nice algorithms developed that would generate this, but not this. But of course, the key difference is that we do want this configuration, just very rarely with a probability exactly specified by the exponential of the action. Whereas here, you never want random noise to be generated if you're trying to generate pictures of people. So one way of trying to address this generation problem using machine learning tools, like's been done for generating these images of faces, is via what are known as flow-based models. And the idea is very, very simple. You're trying to optimize a change of variables. If you have some distribution that's easy to sample from, and you have a function, a change of variables that takes you from that to your target distribution, and then you've solved your sampling problem. You just take samples from the easy to sample distribution, you put them through your function, and then out pop the samples you're interested in. So if you also design this function so that it's invertible and has a tractable Jacobian, then even if this change of variables is not exact, you can still guarantee exactness. You can show that you can create an ergodic and balanced Markov chain out of these independent samples and guarantee convergence to the desired probability distribution in the limit of a long Markov chain just like you do with HMC. And so you can create these very general changes of variables by composing many simple transformations. In particular, if you compose simple layers acting only on parts of the field each time, you can have a nice tractable Jacobian that's lower triangular and easy to invert. And so then you can optimize this function, that optimization is the machine learning part, to do your sampling. So it's worth noting that this is applying this to lattice QTDs, unfortunately, not at all an out-of-the-box application of these machine learning tools developed in industry. Because of course, lattice gauge fields have lots of features that you don't have in, say, images, in particular symmetries. So the physics is invariant under specific field transformations like rotations, translations with our four-dimensional boundary conditions. We have gauge transformations, so where you're changing each link differently based on your gauge transformation. And so if we compare the properties of an ensemble of lattice QTD gauge fields to, say, a benchmark image set for machine learning, you see a number of really significant differences. The first is that a state-of-the-art lattice gauge field is described by something like 10 to the 9 numbers, and we want thousands of configurations, compared to, say, an image described by 3,000 numbers with 60,000 samples available for training. So we have this extreme inverted data hierarchy, which means a lot of machine learning approaches based on training, using training data won't work for us. It's the ensemble of gauge fields that has meaning. Long distance correlations are important as opposed to short distance correlations having meaning like a nose or an eye in an image. And we have these complicated symmetries. So addressing this problem is part of a great collaboration from my group, as well as collaborators at Google DeepMind. Michael Albergo, who's now a grad student at NYU, started with this as an undergrad, Julian Urban at the University of Heidelberg. So great collaboration, lots of fantastic young people, where we've been pursuing this program of how can we use generative machine learned models for gauge field generation. And as I sort of indicated, one of the big challenges is incorporating symmetries. So our field configurations are represented not as in the scalar field example I gave with a number at each site of a lattice, but by links here on our lattice encoded as matrices. So for QCD, we have SU3 matrices, that's 3x3 complex matrices with unit determinant. And so the very first thing is that group valued fields don't live on the real line, but they live on compact manifolds. So we first had to go back and design these sorts of flow architectures on compact connected manifolds, even just the angles on a circle. And then even once you have flows on compact manifolds, well, the action is invariant under group transformations on gauge fields. So gauge transformations. So we had to go back and incorporate symmetries for gauge equivariant flow architectures. And I can't go into too much detail here just because of the length of this talk, but you can see a recorded talk by Tej Kanwar from the Virtual Lattice Colloquium series, which is fantastic. And I can show you an artist's impression of the sort of architectures that we're developing, which are really gauge specific to incorporate these symmetries. And I can show you some of the results. So in an application to U1, pure gauge field theory, we see that training these sorts of flow models really gives you a significant reduction of your problem of critical slowing down, of course, at the cost of upfront training of the model. So here I'm showing sampling of the topological charge, which is the winding number of the gauge field. So the Atiyah-Singer index theorem tells us it's quantized, it's a global quantity. And what we see here, this is on the horizontal axis, the Markov chain step, and on the vertical axis, the topological charge. You can see HMC, hybrid Monte Carlo, so one of the conventional approaches gets very stuck in topological sectors. Similarly, heat bath, here another conventional algorithm shown by the gray line, better, but still very stuck. But the flow-based approach samples very efficiently across this space. So we can turn this into a measure of cost. So here's the integrated autocorrelation time, which you can think of as being a measure of the cost per independent sample in the sampling phase of this algorithm. And here on the horizontal axis, we have beta. So you can think of this as moving along a critical line. You can see that here HMC and heat bath. This is a log axis, so they become exponentially more expensive as you get to larger beta. And the flow algorithm here is reasonably constant. It does increase at larger beta, and that's due to it getting harder to train, but you still have several orders of magnitude more efficient sampling. And I should say that this is a fair comparison in sampling. The cost of one sample from HMC and the flow model is about the same. Heat bath is a bit cheaper, maybe a factor of 2, but you still have genuine orders of magnitude more efficient sampling through the flow model. So this is really a success. This is a proof of principle of an efficient, exact machine learning algorithm for sampling in lattice field theory. We've extended this to SUN. You can see in this paper here, fermions coming soon. And the big question, of course, where significant work is required is, can this be scaled to the size of state-of-the-art lattice calculations? So we have an early science project for Aurora to try to do this and make this a genuine tool for lattice field theory calculations. And it's promising, but there's a lot of work to do. And of course, I should say that although we still face a great scaling challenge, these sorts of techniques really have found interdisciplinary applications. So for example, developing these flow architectures on compact connected manifolds, or something else that lives on a compact connected manifold is the joints of a robot arm, right? Described by angles. And so that work has interdisciplinary applications. These same sorts of ideas have been applied in molecular genetics and drug design problems where the scaling challenges aren't so severe. And so there's been significant advances made through using these sorts of algorithms. So to summarize, I've given really a sort of broad discussion of how we can understand the structure of hadrons and nuclei from the standard model with several very specific examples pulled from some of my recent work. But the upshot is really that first principles QCD calculations are revealing and precisely the structure of protons, neutrons, and even nuclei, both giving us new understanding of the structure of matter from first principles, but also giving us new understanding that we can use to find the physics beyond the standard model, so to constrain beyond standard model physics searches. And then I talked also about, well, how we can try to use new computational tools to push the barriers of what's possible with the limited computation we have available, particularly through machine learning. Well, thank you very much.
Thank you very much, Phiala, for this very nice talk. I clap.
Thanks, Carsten.
It's a strange setup in some sense. Okay, I'm sure there are questions to Phiala. So please raise your hand and then I should be able to allow you to talk. Okay, Manuel. You should unmute your microphone. Yeah, now.
Okay. I have a question regarding this interaction of dark matter with nuclei. This effect that you are talking about, this is distinct from form factors. I mean, form factors have been included for a long time, of course, to go beyond the very simplest point like nucleus approximation. But I guess your effect is a bit more complicated than that.
Yeah, so this is just literally nuclear effects in the scalar matrix element. So not the scalar form factor, just as the scalar matrix element itself, which would affect the whole form factor as well.
Okay, that's a question by Daniel Jenkins.
Yeah, again, when you were discussing the dark matter, especially for the helium case, there were multiple different quark combinations, and it looked like there was much more deviation in the helium case when we expect disconnected contributions, like for when we talk about like individual nucleons, we have the connected and disconnected. And also there was much more deviation for when there is disconnected contributions. Does that connected disconnected thing carry over into the helium case, or?
Let me go back to that slide. Oops, I have a spinny wheel Okay, my slides aren't changing. So your question was for the helium-3, we saw that there were significant nuclear effects in the disconnected piece. That's the case. And of course, which of those different columns of different quark combinations is relevant depends on the exact microscopic model of dark matter that you're interested in. So the simplest thing, of course, is that you would couple to all of the different quark flavors. So strange quarks and disconnected contributions would be important. But here, so this was the flavor separation. You see that the strange quark contributions were much smaller themselves. And so the reason this looks so large is that this is showing the percentage nuclear effect. So you can see the disconnected part itself is only a couple of standard deviations from 0, but it looks, it's much smaller and much noisier. So basically that's not all that's driving these differences here, because it's a small contribution.
All right.
This is many more standard deviations from 0, which is not just driven by the disconnecteds.
All right, thank you.
No problem.
Okay, Chris.
Yeah, thanks, Phiala, for the nice talk. With regards to the machine learning stuff, I mean, obviously this helps you generate a lot of configurations very quickly. I was wondering if you felt like that this would be enough to kind of solve the problem of the exponential growth of the noise of like many nucleon systems, or if you think anything else will need to be done to solve that kind of problem.
Yeah, so it's one aspect of that problem. If you can generate a lot of configurations quickly, you still have to do calculations on all of those configurations. And you still have to have the factorial growth in contractions on all of those configurations. So it's by no means a solution to that problem, but it's, you know, a chunk of the solution to that problem. And the other things we find with these machine learning models is that once you've trained them for one set of parameters, you can quite efficiently move to other places in parameter space. So you want to think about the sort of setup cost as giving you not just one ensemble, but all sorts of ensembles in some region of parameter space. And so you can think about, you know, efficiently trying to do things like interpolate or extrapolate in quark masses via this approach. But no, it certainly doesn't completely solve the problem, because you still need to, on all of those configurations, do all of the work, which is much more expensive for nuclei than it is for nucleons.
Thanks.
Are there further questions? Currently, I don't see any. So then let's thank Phiala again for this very nice talk. And let me take the opportunity to also congratulate you again for this award. I think it's well deserved. And
thank you very much.
I thank all of you for attending this virtual colloquium. I hope you all stay safe and healthy in these times. And I hope very much that we see each other next year, not next year, but at least in 2 years from now at a in-person Lattice conference, hopefully in Bonn. So once more, thanks very much, and bye-bye. Take care.
Thank you.